Hello and welcome to Teaching Mathematics. Today we're joined by Dylan. Hello, Dylan.
The infamous.
Yes. He usually pushes the buttons, but today he's the expert.
Yeah.
Yes, welcome, Dylan.
Thank you very much.
And we've got Kieran pushing the buttons.
Hello.
Now, Dylan, today we're talking about Euclidean geometry.
Yes.
Yes. Now, before we get on to that, why don't you tell us a little bit about yourself?
Well, I started my professional career as a maths teacher. I taught for about 7 years at Greenside High School.
Yes.
But in that time, I slowly began to migrate out of the maths classroom and into the computer lab. And after my time at Greenside High, I came to work at Mindset in a very different role than what I'm working in now. Back then, I was responsible for designing the knowledge management system, the first knowledge management system for Mindset. And I've had a couple of jobs within the company since then. But through that entire journey, education has remained my central passion. And I think the more I work with technology, the more central education and good teaching and learning becomes, because I've seen far too often how technology can be a really expensive and quite disastrous distractor from good quality teaching and learning.
Yes. Very true. Yes. Now, why do you know so much about Euclidean geometry?
Well, I taught Euclidean geometry. I taught it for a number of years. I taught it at grade 10, 11, and 12 level. And it was actually one of the favorite parts of the curriculum for me to teach, because it wasn't so much about teaching maths as it was about teaching skills.
Yes.
Yeah. So I've always enjoyed Euclidean geometry. I was really, really glad to hear that it came back into the curriculum a couple of years ago.
You must have been one of the very few teachers out there who were...
Maybe. And I know that there might be a lot of teachers out there who hate teaching Euclidean geometry because they themselves find it difficult. But hopefully, just as we unpack it today, maybe we can allay some of those fears as well and put to bed this notion that some people can and some people can't.
Yes.
One of my mentors at Greenside, my head of department, would often say, you know, you really, really need to be good at Euclidean geometry because you need to be able to construct arguments. And everyone needs to be able to construct arguments because everyone has people in their lives that they need to argue with from time to time. So I mean, it might seem like a silly or frivolous example,
yes.
But it certainly does, I think, pack a punch.
Oh, I do think so as well. And remember, if you want to join the conversation, please do. Find us on Facebook at Digital Classroom South Africa. And Kieran will be watching the post over there. Just make a comment underneath the post, and he'll let us know. Also on Twitter, use the hashtag MEMaths, as well as the chat box underneath this window. So you scroll down, you see where it says nickname, you plug in a nickname, you press log on. That way you don't have to sign up for Twitter or Facebook, and you can still talk to us. And remember, you can win money. Well, airtime.
Airtime, yeah.
Yes, 110 rands airtime for talking to us. So do it. Okay, now Dylan, as you know, I've been reading this book. Oh,
I know so well, yes.
Yes, and we've been through the steps or techniques one by one. It's called Teach Like a Champion.
Yes.
And Kieran's going to pull up the slide for us now. And we're on technique number 18. And it says check for understanding. The little blurb about it says check for understanding and do something about it right away. Basically, if you feel like someone's not quite getting it, you remedy it immediately.
Yeah.
This then poses the question, though, how do you check for understanding? Are you checking by testing? Are you checking by question and answers in class? Are you checking by just looking over a shoulder? How do you always check?
I think all of those are valid. The one thing I would want to add to that statement is check for understanding often and remedy or do something about it straight away. I mean, for me, I think it's a really silly idea to launch into a lesson, go down the road 40 minutes and actually not know whether you've been scratching the itch or not. I think all of the things that you mentioned are spot on in terms of checking understanding. I think you can ask questions, but very often the best questions to ask are not the ones with a yes or no answer. They're the ones that require the learner to actually give you a little bit more.
Yes.
Sometimes you can check for understanding by asking a learner to explain something that you've just said in their own words. So that's not a question. That's just putting someone else on the spot and having them not regurgitate, but just give back to you what they think you've said. And that's very often a very good way to check if somebody that you're having a conversation with is understanding. Well, I think I hear you say this. Formal testing is obviously one way, but that's often too late.
It takes a week to mark things.
It takes a week to mark things, and often you've got a couple of lessons under the belt before you've found out that there's some really, really big problems.
Yes.
Group work, I think, is a great way to check understanding, to have learners talking with each other and for you to be eavesdropping on the conversation.
Yes.
I think there's simple techniques like just show of hands, rather than calling out. Who of you thinks the answer is A? Another technique that you can do is hold up a piece of A4 paper with the answer on it, so no one feels like they're being exposed. And at a snapshot, you can get an indication of who's with you and who's not. There are obviously higher tech versions of that using sort of clicker systems and that. But if you don't have those, a piece of white paper does a great job.
I would actually say that colored paper is easier for a teacher.
Perhaps it is, yeah.
But then you don't have the non-anonymity.
Yeah, you don't have the anonymity, sure. Sure.
Yeah.
Yeah.
So that is a problem. I do remember one of my lecturers saying that the worst question you can ask in a class is who doesn't understand.
Well, yeah, it's almost a meaningless question because it's not going to give you any actionable intelligence. It's not going to give you anything that you can react to. But if somebody says, well, I don't understand this, or you can hear in their explanation, or you can see in a question that they've answered what they don't understand, well, then you're starting to know where the problem is.
Yes.
And you're starting to be able to diagnose where you need to dive into. Rather than starting at the beginning, it might be just a little thing somewhere in the middle that you need to correct.
Yes. I do remember children coming to my class, first year teacher, and saying, I don't understand algebra.
I don't understand anything. Yeah.
And so then I would start at the beginning, 2 apples plus 3 apples equals... And turns out it was just taking out a common factor that they didn't get. So it's important to check all the time so that you
Absolutely.
know where they're going wrong.
Yeah.
Yes.
Yeah, and I think that's a critical part of the teaching and learning process. I think so often we can get stuck into this delivery mode that we have to be up there talking. But I think teachers need to spend a lot more time listening. And not only listening with their ears, but listening with their eyes as well.
Yes.
I think how people are sitting in your class, how they're behaving in your class can tell you an awful lot as well. You can be delivering what you think is a wonderful, wonderful lesson, hugely exciting because you find the subject matter interesting.
Oh, yes.
But if someone is kind of dazing out the window or falling asleep, you know immediately that something's going wrong, and so you need to course correct.
Now, you started off by saying that there are key skills here that you would like to emphasize in this section. Now, we do know that geometry, Euclidean geometry, has been taught in term 2, I think,
Yes.
for 2 or 3 weeks.
Yes, that's right.
So this week is pretty much just a week of revision.
Yeah.
So we should have all the content there.
Well, it's not necessarily just a week of revision. I think it's a week of application. And one of the ways in which I like to look at Euclidean geometry is as a toolbox of tools.
Okay.
And every theorem, every statement, everything that you discover to be true is just another tool that you can put in the toolbox and use at a later time.
I wonder if students would get the analogy of a toolbox.
Maybe another analogy is it's an app on your device, and you need to solve this particular problem. Well, that's going to be the app, that app, and maybe another app that I need to use to solve this particular problem that I have. But
Yeah.
Anything that's going to give learners the sense of, well, I've got these things at my fingertips, and I don't need them all the time, but I need to know how to use them, and I need to know what they can do for me, so that when I'm faced with a problem, a ride, or whatever we want to call it, I've got an instinctive feel about, which tool is going to be beneficial here, and I can try and use that tool.
I think you could have a lot of fun with that app analogy. You could make
Probably
a poster with all the different theorems that you can use, have it up so that
Absolutely.
they're constantly reminded of what's there.
and add to it constantly. I think in some of the previous webinars that we've done, teachers have recommended that learners keep a book, like a cheat sheet or something like that.
Yes.
Maybe people don't like that particular term, but maybe you can make that toolbox analogy tangible. And maybe it's in the form of a book. Maybe it's in the form of a Tupperware, and you just put little cutouts of each of the theorems inside the Tupperware. Whatever you think is going to make it real and tangible and
Yes.
practical for your learners, well, explore with that. You might find that some learners in your class want to do it in a book form because that's how they think. Other learners might want to do it in a Tupperware form. Other learners might just want to have an audio track of the theorems being read out. Whatever makes sense to their learning style. But I think in all cases, the analogy holds. And that's really what excites me about Euclidean geometry is you're never going to use this in real life. Okay, let's just get that clear. This is not something that you're going to go out and find a job solving Euclidean geometry riders. And when you say that to learners, very often they'll say, well, why do we learn it? Why do we have to do it? And the answer to that, I think, is really, really simple.
Yes.
You're doing it not really for it. It's just an end. It's just a means to an end. And the end is being able to think, being able to look at a problem, dismantle it, break it up into its constituent parts, understand each of those parts, and then start to solve that particular problem.
Okay, let's take a look at the slide that says key skills. The first one is, I'm going to read out the words and then we can talk about them in general. We've got reason, generalize, conjecture, investigate, justify, prove, and explain. These are all words that you would find in problems, wouldn't you?
Yeah, they are. They're very much taken from the language of the section. And I think that language is used purposefully because these are some of the skills that we're trying to teach learners, or that I think we're trying to teach learners. If you never ever remember what the 4 rules for congruent triangles are after you leave school, well, who cares?
Yes.
But do you leave school with the ability to look at a problem, pull from your mind things that you think are going to be useful to solving this problem, and tackle it? And I think that's what we're after in this particular section.
Now, before the show, we were talking about this, and you said that it could be applied to arguments, and we spoke quite a bit about how it would be applied to arguments. Why don't you explain that a little bit more so that we can explain to learners why this...
Okay, well, I mean, let's take a subject like English.
Yes.
Or even history, where part of the skill base that we're trying to teach learners there is how to construct an argument. How to take some facts, some opinions, and how to put them forward in a way that is going to communicate what you want to communicate clearly and unambiguously, in a way that's going to try and persuade somebody of your point of view. Now, what's really interesting about mathematics is that very often the persuading is very simple, because it's black or white in many cases. It's true or false.
Yes.
But it's that constructing of that argument. Step 1 leads to step 2. If step 2 is true, then step 3 must be true. If step 3 is true, then step 4 must be true. And so you construct this argument step by step by step in a logical way that there are no gaps. Anybody looking at previous steps in the argument can't push holes into it. Mm-hmm. And very often, if you're able to get that argument strong from the beginning to the end, well, then it becomes a very persuasive argument. But if your argument has weak roots, weak foundations, well, then it's not persuasive at all.
That skill is extremely important in business, if you go into law, into marriage.
Marriage, yes. Yeah.
Everything.
And I think in geometry it's just a case of, well, we're going to use this as our canvas. We're going to use riders and proofs and theorems as our tools to construct an argument. But I think the same things apply. If this, then that. If this is true, then that is true. And what makes that link strong? What's the reasoning behind that link? And I think that's where the real power of teaching Euclidean geometry in this way comes into its own.
Yes. We were going to go to the 5-point teaching strategy, but I'd actually like to take us to the 3 pressure points first, and then go back to it.
Sure.
And so on the slide we have the first one, which is you either got it or you ain't.
Yeah.
Yes.
Well, and I think Lee in a previous webinar said the same thing, that there is this notion that some people can do geometry, some people can't.
Yes.
But that's tantamount to saying some people can argue and some people can't. Or some people can think logically and some people can't.
Well, that's debatable.
Perhaps. But I think if you were to construct an argument to convince me of that, it would have to be a really, really powerful argument.
That's very true.
That there are some people that just simply cannot think logically, ever. There may be times when emotions are high,
Yes.
and you're in the heat of an argument where logic may become slightly less important. But I don't think that diminishes anybody's ability to think through something logically, and that's
Yes.
really what we're after here.
I think the danger with this kind of thinking, you've either got it or you don't, is that when someone finds Euclidean geometry too easy, like maybe myself in high school, I used to think, well, this is meant to be difficult. I'm finding it too easy, so I must be doing it wrong.
Yeah, maybe.
And then I just left it out. I must be honest. In
Really?
high school, I'd left the section out completely because I thought I've obviously got something wrong.
I struggled with the section in high school. Not because I couldn't construct an argument, I don't think, but often because in the heat of an exam or a test, I often got so flustered. I didn't have a method of going through, calming myself and thinking through the problem systematically, that I would kind of just dive in and be lost at sea. And I think we'll get onto some of those techniques to prevent learners getting into a frenzy and getting the emotional
Yes.
response too high. If
That's
we can
very important to teach, isn't it?
Yeah, keep the emotion out of this. Everyone can do this. Maybe there are going to be days where you just can't see it, but that doesn't diminish you as a person. That certainly doesn't diminish you and your ability to think through and reason logically.
Do you really think everybody can do this?
I think everybody can do it. Yeah. I think some people might be more proficient at it. I think some people might be quicker at it. I think some people might find it easier. But I do not believe that anybody absolutely can't. Unfortunately, the way that we seem to test standardized tests around the world is we tend to advantage those
Yes.
that have the natural inclination because there's a time pressure to this thing. I would love to see a geometry exam given where you get given the paper and you take as long as you like. And I'd love
that
to see
would
the
be
results
wonderful.
that come out of that.
Yes. I had a thought to follow on with that, but I've got distracted now.
Okay.
So let's go to the next one. Problem-solving skills take time to bake. What do you mean by this?
What I mean by that is this is not a quick thing. Problem-solving skills, I think we're learning right from the time that we're born. We're learning to look at the world, investigate the world, generalize the world, problem-solve the world.
Yes.
So to think now, well, we can take our grade 10 learners, and in a week, we can just do this. We can just nail it. I think is unrealistic. And I understand that the curriculum has to kind of conform to some sort of time structure.
Yes.
But that doesn't necessarily mean that you can't be doing geometry throughout the rest of the year. It might be a bit late now for this particular academic year, but there's nothing stopping teachers, I think, beginning of next year, slowly and just consistently building up these skills, because they do take a while to bed down, as I say, to bake. These things don't often come instantaneously.
I think that links up, the idea of doing a problem every week links up really nicely with the next point, which says geometry is not algorithmic. And a lot of the stuff we do in mathematics is. And as a result, our number sequences links nicely to our functions and everything else. So you're basically teaching the same skills over and over again. But geometry feels like this isolated
It's almost
thing.
like, it's like the poor stepchild.
Shame.
Shame. And I think that is one of the pressure points that people have historically found with geometry is you can't reduce it to a set of predefined steps.
You also can't teach it like it's...
You also can't teach it that way.
That.
It doesn't allow itself to be boiled down to a recipe. And I mean, honestly, that's the way I got through some mathematics courses at university. I didn't understand what I was doing. I just knew that I had to do these steps and I would get sufficient marks. Geometry, unfortunately, just doesn't work that way because it's not about following a recipe. It's about taking an assemblage of tools and picking the ones that you're going to use to solve this particular problem at this particular time. And so I think that is a pressure point, and we need to be mindful of that we shouldn't be teaching this algorithmically, because I think we're doing ourselves and our learners a huge disservice because they're not going to learn the skills for which geometry is in the curriculum in the first place.
I remembered my point, the analogy. Everyone can do geometry just like everyone can throw a ball across a field. Mm-hmm. Some of us will get the ball across the field in one throw, but others, like me, might take 20 throws. Throw this and then walk to that point,
Perhaps,
throw to the next one. but you will eventually get there.
Might take you a little bit longer.
Yes.
Sure.
Okay, 5-point teaching strategy. Get all the basics in place, triangles and quadrilaterals. And that's the first point on the 5-point teaching strategy.
So really at this point in the year, we've done term 2, we've looked at triangles, we've revised congruency, similarity, we've looked at the properties of quadrilaterals, we've looked at the midpoint theorem. Those are all tools.
So it's the content that we're going to use.
It's the content that we're going to use. So at this point in the year, my advice is just make sure that those tools are in the toolbox.
Yes.
And that learners know what they look like, know what they are, know how to use them. Because what term 3 is really about is then applying those tools.
Yes.
That's what the curriculum document says, is solve riders, solve problems, using all the stuff that you've learned to date.
Okay, and just to confirm, riders are geometry problems.
Geometry problem. And I do not know why they're called riders, but I really, really think we should find out.
One day.
One day.
The second point says, work with theorems intuitively, measure, explore, discover, and generalize. There are those words again from the key skills.
Yes. So, and I think a lot of this mirrors what Lee was saying as well. But my sense of this is, it's nice to be able to prove a theorem, but it's, I think, better for that theorem to be a friend. And let me try and explain that.
Yes.
To almost have an intuitive sense of what this thing is saying, what this thing is doing, and what this thing means. Because I think what proving the theorem up front often does is it makes it algorithmic, it makes it formulaic, and it reduces this process of thinking through to, well, I must just learn the theorem, and I must just learn all the steps. And goodness help me if in the exam I can't remember all the steps. Because that was certainly the advice that I was given when I was a learner. And I think that that's wrong. I think it's far better if learners understand what the theorem is doing and understand what it means, even if they have to draw pictures and they measure and they discover some of the properties that the theorem is talking about, whichever theorem it might be, for themselves. They can prove it later, and we'll get onto that, I think, in a moment.
Yes.
But just having this guttural sense, almost.
Now, I know later on we have some slides which are going to talk about how to develop that. So we're going to leave that there for now.
Okay.
And we are going to discuss it more just now and go through the last 3 points very quickly because we're also going to talk about this later.
Yeah.
And they're quite closely linked to Lee's ideas
very,
as well.
very similar.
So if you haven't seen Lee's show, please go back. I'll put a link to it
put the links in the blog
and watch it as well. It's worth a watch, I think.
I think it's worth a watch.
Yes. Okay, so the third point says apply theorems to numeric problems, then apply theorems to abstract problems, and the last one, prove theorem formally. Traditional teaching says that we should do the theorem first and then apply it to all sorts of things. So this is upside down.
It is upside down, and one of the reasons why it's upside down is in terms of pure mathematics, you don't want to be going and using some statement to prove other things unless you're absolutely sure that that statement itself is correct.
Yes.
And so I think that there's value in just highlighting that fact to learners while you're teaching. That let's just assume for the time being that this is always everywhere true, and we're going to use it, and we'll just satisfy ourselves that it is always and everywhere true later on, so that we don't get sidetracked by that.
Yes.
So a pure mathematician would want to just get the foundations done first. Can I always assume that this thing is true? Whereas I think in the case of school mathematics, I don't think we're as concerned with the rigors of pure mathematics, particularly in this section. I think we should be more concerned with the skills that we're developing.
Okay.
And so the reason why I say, and I think I agree with Lee when she says apply the theorem to numeric problems, is that's often an easier place to start because you've got something that's concrete.
Now, I wonder if you're doing point 2, which is work with theorems intuitively, whether you need to force them to, well, not force them, but say, just trust me, this is always right. Because they have proved it to themselves that the theorem will always be true. They just don't have the formal proof.
Yes. And I think there, again, is a really useful lesson that they might have convinced themselves that something is always true, but that doesn't necessarily mean that it's always true.
Yes.
One counterexample will throw all of that work out of the window. And there are certain things. The one example that's really great to kind of do this with your kids with is one of the congruency rules, side angle side.
Yes.
Where the angle isn't between the two sides.
Yes.
And get them to like construct all these triangles where the angle isn't between the two sides and convince themselves that all of these triangles are congruent. And then you throw the one counterexample in, and it just blows everything out the water. And that could be a useful lesson to show them that no matter how many times you draw the shape, no matter how many times you measure the shape, no matter how many times you think you've done this, it's not a formal proof until it's been proven in the general case. And that, I think that also comes back into other parts of the curriculum. Calculus is certainly one, where we use the rule, and that's great, but can we prove that that rule is always true in the general case?
Yes.
And so I think that that's what this is saying. And just for grade 10, 11, and 12, where we're not necessarily that concerned about formal mathematics, I think it's fine to leave the formal proof to the end.
I do wonder about the side angle side thing and then throwing all of the things out of the water. I wonder if it would shake their confidence if they suddenly are thrown.
It might. I think that there is that potential for some learners to be shaken by that, but I think you can do it in intelligent ways. I think you can create a safe environment where you're not belittling them, where you're not saying that all of the work that you've done is useless, therefore you are useless. I think you can simply use that opportunity to state the fact that, we did some really good work here. We were so certain that this thing was always true. But look at this one example. Oh dear, that means that this thing isn't generalizably true until we've proven it in the general case. And the curriculum speaks to that point exactly in term 2. And it highlights that for us. And so in the curriculum document, if it's highlighting that point, it's got to be important.
Yes.
And it's got to be really important for learners to understand that as well.
Shall we look at some of these?
Yeah, sure.
How to teach intuitively. Now, we're going to start with a slide that says basic lines, and Kieran's pulling it up for us. Tell us about basic lines.
Okay, so these are some of the basics and that have come from many years back, and I'm just going to draw it here on the board. So you have two lines that are cut by a transversal.
Yes.
Okay, and we know immediately that certain things exist. We know that we've got that angle, and we call them co-interior angles. We know that we've got that angle. Maybe let me use a different color. We've got that angle and that angle. Now, I'm not using exactly the same shapes for a reason. They're alternate, and we've got the corresponding angles as well. Those angles always exist.
Yes.
They don't just magically appear. They always exist when you've got two lines cut by transversal. What becomes interesting?
The next slide.
Is when those lines are parallel. Then things become interesting, because then we can say certain things. So let me just quickly draw. So we've got parallel lines. They might not look parallel to you, but believe me, they are. I'm well practiced at this. So we've got the corresponding angles, we've got the alternate angles, and we've got the co-interior angles over there, and they're adding up to 180 degrees. The corresponding angles are equal.
Yes.
When the lines are parallel. The alternate angles are equal when the lines are parallel. And the co-interior angles add up to 180 when the lines are parallel. Those angles always exist, whether the lines are parallel or not. But the fact that the lines are parallel means that the alternate angles are equal, corresponding angles are equal, co-interior angles add up to 180.
And that's why when you write the reasons, you need to state which lines are parallel.
You need to state which lines are parallel, because that's the basis of your argument. I can say with confidence that these two angles are equal because the lines are parallel.
Yes.
If the lines were not parallel, those two angles would still be alternate angles.
Yes.
But they wouldn't be equal alternate angles. And I think that's often a very subtle shift that learners miss and that we don't reinforce enough.
No, we don't. I can't actually ever remember
The alternate angles are always
talking
there,
about that.
but they become equal when the lines are parallel. So I think that's the one important thing, just to make sure that that basic is in place. And not the fact only that the alternate angles are equal when the lines are parallel, but the reverse. If the alternate angles are equal, then the lines are parallel.
And I know in the slide you put the if this then that.
The if this then that. The it. And so I guess what I'm suggesting is focus on this and repeat it often, not just with angles and lines, but with triangles and with quadrilaterals. This thing of if this then that. If this is true, it means that these things are true. So if the two lines are parallel,
yes,
it means that the alternate angles are equal. It means that the corresponding angles are equal, and it means that the co-interior angles add up to 180 degrees.
And if alternate angles are equal,
it means the lines are parallel. Therefore, the corresponding angles are also equal, etc.
So they need to go both ways.
They must be able to go both ways, and that's a crucial skill that we need to develop as early on as we can. If A is true, then B is true.
I wonder if it would be worthwhile in that toolkit or the cheat sheet or something, having a definition that says when two lines are parallel, the alternate angles are equal, but then right next to it saying when the alternate angles are equal, two lines are parallel.
Could be, absolutely. So
making it as explicit as that.
So that learners can move backwards and forwards. When B is true, then A is also true. And that's one of those techniques that we'll get onto in a moment that's so important in solving geometry problems.
Well, let's go on to the next slide.
Okay.
And we've got basics triangles.
So this is another basic, and we're not going to go through what all the properties of the triangles are, but these are the triangles. It's safe to say the if this then that sort of proposition needs to hold here as well.
Okay, so
if the two angles in a triangle are equal, then it's an isosceles. If it's an isosceles, then the two sides in a triangle are equal, and the two corresponding angles in the triangle are equal. So if this, then that. If that, then this. And learners need to be equally familiar with both.
Yes.
Yeah.
So constantly
reinforce
bringing that up.
Yes.
Okay, your key skills that you spoke about in the beginning. How would you apply that to these kinds of triangles?
Well, let's just quickly jump back to them.
You've got reason, generalize, conjecture, investigate, justify, prove, and explain.
So one of the things that you might have done in teaching the properties of triangles is having learners draw the various different kinds of triangles and then have them measure some of their properties. So in that case, they're investigating.
Yes.
The trick then is in generalizing. Well, does it always mean that if these two sides are equal, that it's an isosceles triangle? Well, in this case, yes, because that's just a name that we give to that kind of triangle. It's a shorthand, if you like. So instead of having to every time say, given triangle ABC where AB is equal to AC, we can say, given isosceles triangle ABC.
Yes.
And you can just mark which of the two sides are equal.
We often talk about mathematicians being lazy. So this would be an example. Well, not lazy, efficient.
Efficient, yes. I think that's the word we used.
This would be an example of that kind of thing.
Yeah.
Instead of listing all of the properties of an isosceles triangle, we
every
just
time
say it's an isosceles, so we assume all of these properties apply.
And so that exact reasoning comes into some of these other skills, the justify and the prove. And what's really I love about geometry is that it builds on itself so beautifully, right from the first time we ever talk about lines and angles down in primary school. All of that understanding comes with and is as useful as the circle geometry theorems.
Yes.
Because none of the circle geometry theorems work unless some of those foundational theorems are true.
Yes.
And that's what I love about it. It reinforces and it gives value to some of these simple things that we kind of take for granted sometimes. The corresponding alternate angles are equal.
Vertically opposite
opposite angles are
yes.
equal. But what's so beautiful about all of this is that is just then another tool. It might be a small, might be a relatively insignificant, but in the grade 12 rider, it might be the tool that unlocks the rest of the problem.
How many times does vertically opposite angles come up in grade 12?
Yeah.
Meanwhile, I think it's grade 9 that it's taught for the first time.
I think so.
Maybe even grade 8.
I'm not entirely sure, but it's definitely in the senior phase.
Okay, now we've got a slide up that says basics, congruency, and similarity.
Yeah.
And this, of course, is the SAS.
This is the SAS example, yeah.
Yes.
So, again, it's the if this, then that. If we've got two sides and the contained angle equal, then the two triangles are congruent. If the two triangles are congruent, then all three sides are equal, all three corresponding angles are equal.
Now, you would use this to teach the intuitive understanding or working with the theorem.
Yeah.
Okay.
Yeah, absolutely. So in this instance, learners can construct the various triangles. They can maybe sometimes not have the angle included, as I said, and then you can show them the counterexample.
Would they do this alone?
I absolutely have them do this in groups. I think geometry is one of those times, one of the best times in the curriculum for group work, because a lot of it can be discovered by learners. And often the best discoverers for each other are learners, rather than the teacher from on high saying, well, this is true. If I can discover it for myself as true, somehow it just tends to stick.
It has more value when they discover it for themselves.
Yeah.
Yes, it's almost like they paid for it with hours and sweat and tears.
Yes, it's almost they have a sense of ownership of it. So I would absolutely suggest a whole lot of group work in this section. Get learners to solve problems, get them to construct, get them to measure, all in groups. A useful technique is get different groups to do slightly different things, so that at the end of that activity you can compare, and you can then start to make some generalizations, perhaps. That everyone was working off these basic guidelines, but oh look, everyone has basically constructed the same thing.
Okay.
So now we can start to generalize, and because of that generalization, when we've proven it, well, then we can start to prove other things with it.
And when we were talking about this earlier, you spoke about doing it with parallelograms.
Yes, absolutely. Yes. And I mean, maybe let's quickly get there.
Okay.
So for quadrilaterals, again, not to go through all of the properties, but a useful technique I have found in helping learners understand the properties of the various quads, which they need to know. They need to know personally, because they're going to need to use those tools. It's pointless to know for its own sake that all angles inside a square are 90 degrees. Who cares? Really? I mean, we intuitively know that from even before school. I mean, it's a nice piece of knowledge to have in your head, but I think it really becomes into its own when we can use that piece of knowledge to solve something that's a lot more complicated and a lot more complex. And that's the problem-solving skills I think we're after. So for quadrilaterals, basic quadrilaterals, any closed figure with four sides.
Yes.
Yeah, we know that. Learners know that, or they should know that. If they don't, then let's reinforce that. Have them maybe construct some quadrilaterals. And you can see that out of a class of 40, everyone will construct a four-sided closed figure, but they'll all be different. But what's common about them? They all have four straight sides, and it's a closed shape. Great. But now, what happens if we start to impose some restrictions? Two of the sides must be parallel. Well, then we get
a trapezium.
What happens if we impose some more restrictions? Both pairs of opposite sides must be parallel. Well, then we get a parallelogram. What happens if we add some more restrictions? Well, all the interior angles must be equal to 90 degrees.
Yes.
And then we get a rectangle. If we impose some more restrictions, all the sides must be equal.
Yes.
We haven't said anything else. Well, then we at least get a rhombus. And all the sides must be equal. And all the interior angles must be 90 degrees. Well, then we get a square. So, I hope that just through this we can see that the one thing builds upon the other. And all the properties of a trapezium are properties of the square as well. Because a square is just a special kind of trapezium. The same way that a trapezium is a special kind of quadrilateral.
Now, I understand doing this kind of activity, and I think it's very, very valuable. But what it is missing are the properties of the diagonals.
Absolutely. Then that becomes a really interesting activity for learners to go and discover. So if we have a parallelogram, what can we say about the diagonals? Are they the same length? Do they bisect each other? At what angle do they intersect? How do the properties of the parallelogram's diagonals differ when we impose the additional restrictions to make the parallelogram into a square? And have them discover that. Now, a lot of this would have had to be done in term 2.
Yes.
Okay, I mean, there isn't really time to do it now. But certainly if there is time now, or even as a homework exercise, as a reinforcement exercise, it might be really useful to give this as an activity to learners to do at home, to say, I want you to go and construct all these shapes, and I want you to answer the following questions about them. What can we say about their sides? What can we say about their internal angles? What can we say about their diagonals?
So that would link back to the skill of generalization, which is one of the key skills you mentioned at the beginning.
Absolutely.
And conjectures, drawing conjectures.
And drawing conjectures, yes. Because what it means is, now I'm conjecturing that all the properties of a square are also properties of a parallelogram, for example. And I can test that. And I can see that, yes, they are, every single one of them. Because the square is just a really special kind of parallelogram.
Yes. Okay. Shall we move on?
Right.
And then we've got...
then we've got the kite, which, it doesn't fit into the family nicely. But it's an interesting shape. It's a very interesting shape. And it's kind of halfway there between the rectangle and the rhombus.
And that's because the diagonals bisected 90...
Well, the square's diagonals bisected 90.
Yes.
Yeah.
And the rhombus.
And the sides are not parallel.
Yes.
That's the key difference. They don't have to be parallel sides. Whereas all the other shapes, really from trapezium down, there's some sort of parallel side thing happening.
Okay, we have 20 minutes left. Shall we go through... Now, we spoke about numeric versus abstract problems in a previous thing. Why don't you define for us what you mean? What is the difference between a numeric and an abstract problem?
Well, a numeric problem is one that has numbers or one that can be reduced to numbers. Whereas an abstract problem is one that works with the general case. So it's not actually going to give you any lengths or sizes of angles. It's going to give you it's going to ask you just to work in the general.
Okay, so side AB. Side
AB is parallel to side BC. What can you therefore say about EF?
Okay.
If that's the particular question. So there's nothing concrete in the question. And we know as teachers, we know as maths teachers, that one of the best ways to help learners understand stuff is to always move from the concrete to the abstract.
So from what they can see and touch and hold to something that's up in the air somewhere.
Yes. Yeah. And that's why we introduce algebra quite late in the schooling curriculum, because that ability to work abstractly doesn't exist in young minds. They are very concrete. And to get young learners to move just from the concrete representation of two blocks to the concept, the abstract concept of two-ness, can be quite a jump.
Yes, I like the way you've described that.
So it's that constant move, and that's why mathematics is so powerful, because it doesn't deal with the specific here and now. It's always striving to generalize.
Yes.
It's always striving to the abstraction, to saying, well, it might be true then, but is it true always? Or it might work here, but does it work everywhere? And that's what's so powerful about mathematics. But that conceptual understanding that working in the abstract is difficult. So it's often easy, and educational psychologists have known this for decades, that if you start with the concrete, there's a sense of familiarity, there's a sense of, security, that then helps us to take that leap into the abstract.
So let's look at a numeric example.
So here's a numeric example.
We've got a picture of a parallelogram, 2x, x, and 120
we have to stop you there.
Why?
We don't have a picture of a parallelogram.
Oh, I've made...
We have a picture of a quadrilateral with one pair of opposite sides parallel. So at best, right now, we can say that we've got a trapezium.
Yes.
It looks like a parallelogram, and that's something that learners so often make a mistake of, is, well, it looks like a parallelogram, therefore it must be a parallelogram. But Not
You see, I've already calculated the size of
that's
X
what you've
and
done
then
already.
yes.
Yeah, you were just way ahead. But here's an example of a numeric question. So we've got 2x and x and 120. So we've got numbers.
Yes.
So some of them are algebraic,
Yes.
but they're still numbers.
Okay, so talk us through it. The first question says, using the information provided on the diagram, prove that AD is parallel to BD. And by talk us through it, I don't mean talk us through the problem. I mean talk us through how you would teach it.
To learners?
Yes.
Okay. So in this case, we know that we've got two sides parallel, and we have to then prove the other two sides parallel. So in this case, we've got 2x and x, and we've got another angle of 120.
Yes.
So we could do some construction. Maybe we could draw in a diagonal. Or we can take the fact that, we've got two parallel lines already. So we know something about co-interior angles. So we can do some work with x. We can discover what x is.
Yes.
Because we know that 180 minus 120 is equal to x. And if we've got x, well, we know what 2x is. And if we know what 2x is, well, then we can say something about those two angles. And if the angle at A and the angle at B, let's just pull this up on screen, Karen. We need to see this picture. If we've got the angle at A and the angle at B, we know what those two angles are. If they equal 180 together, well, what can we say about the line AD and the line BC?
So basically, there are quite a few ways we could tackle this.
Yeah, a number of ways.
And it's important to make that clear when you're teaching it, that Billy is not going to tackle it in the same way as
in
Bobby.
this particular example is probably only one way, that you solve for x and then you solve for 2x, and you figure out that 2x plus x equals to 180. So we've got co-interior angles equaling 180. Therefore, like we were saying in the beginning, if this then that, well, if the lines are parallel, then the co-interior angles are 180.
Yes.
If the co-interior angles are 180, if the sum is 180, well, then the lines must be parallel. And if the other two lines are parallel, well, then we can answer B.
Yes.
And then we know that it's a parallelogram.
But even in the act of solving for x, you could do it in one of three ways.
Show me.
Well, we have co-interior angles
Yeah.
with 2x and x, so that means they'll equal to 180.
No, we don't. We don't know that 2x and
That's very
x
true.
are supplementary yet.
I did it again.
You did it again. We don't know that they're supplementary yet. So we have to work with what we
So there is only
absolutely
one
do
way
know.
to solve.
There is only one way to solve it.
Okay, now previously, and I know many teachers will tell their classes this, that if there is a part B to the question, it usually relies on part A,
Yes.
the information from part A.
Yes.
And it's important to tell your learners that if they haven't got part A, they must just assume that what they've been asked to prove is
Yes.
actually correct.
Yes, so if they're in a test or in an exam and they can't do A, you just can't see it. Leave a blank space, go on to B, and use A.
Yes.
Just say, proven, above. Okay? I know I didn't actually do it, but I'm sure it's true because you wouldn't have asked me to prove it if it weren't true.
Yes.
So absolutely. And that's a really helpful technique. And it just takes some of the pressure off that, I just can't do this. Doesn't mean that the rest of the question is inaccessible to you.
I think when you're setting questions, though, you must also be careful that the first question isn't relying on you finding the size of an angle, then the second question relying on that size of the angle that's in part A, because then your marking is going to be a pain.
Well, if it's a numeric question, yeah. But if you do happen to set that question as a teacher, then you need to suffer the consequences for it, and you need to work through the answer.
Yes.
You can't penalize learners for the fact that you set that kind of question.
Yes,
Yeah.
you have to mark according to what they got in
Yes.
part A.
Absolutely. And work their error through. Because, again, what we're after here, and if you look at any geometry memo, we're after the thinking. How are you approaching this problem?
It is an abstract problem.
So this is an example of an abstract problem. It's a relatively simple abstract problem. Both pairs
Yes.
of opposite sides parallel. Sometimes it's congruent to triangle CHB.
Okay,
Okay, so that's,
for angles
we have
rather
no
than
idea what
X
size they
and-
are. We have no idea how long the sides are.
That's a great idea.
Answer that. Because I think this one is a little bit more challenging because they haven't given you any of the information on the diagram. And so there are some techniques, I think.
Drawing.
Okay, so we've got K and L and M and N.
And we are told that it is a parallelogram.
We're told that it's a parallelogram. Right, we're going to fill that in now. We've got the diagonal. Okay. And
we need to draw that just a little darker.
Oh, is it? How's that?
Much better.
Is that awesome? Okay. So then we have this perpendicular. We know it's a perpendicular because they tell us.
Yes.
And we've got this perpendicular. We know it's a perpendicular because they tell us.
Okay.
And we've got angle 2 and 1 and 1 and 2. Okay.
Yes.
And the words carry enormous meaning.
Now, Lee has said before that one of the biggest difficulties is
parallelogram. KLMN is a parallelogram. Now, this side is parallel to this side, this side is parallel to this side, and this diagonal does this with that diagonal. Immediately, that side is parallel. And in that case, I think a great middle ground is you might have your pristine, like a parallelogram.
Yes.
Okay, importantly, because we were dealing in the abstract and them. Not because they felt like it, but because that's information I need to point you in the direction it wants you to go.
Yes.
In this case, perpendiculars, we've marked those in. Answer the following and give reasons. If I can't do part A, I can still go to part B, because I'll just assume that part A is right.
Yes.
Okay, so in this case, side, I got side strategies available to me. I need to pick one. And down, there's a whole bunch of tools in the toolbox I know I don't need.
Yes.
And pull these out.
Yes.
It's candidate. So let's try that one. Okay, so I know that this angle here, and I might need to mark it on my diagram so that I can describe which angle I'm talking about.
Yes.
I know that y2 is 90 degrees, and I know that x1 is 90 degrees. So I know immediately that that is equal to that, and that is equal to that.
Because it is
Side. So it's either this side, yn, and lx, or that is the same length as that. So I'm going to look at that. But the technique that we need as teachers to empower them with is, well, you've explored 1 of 4. So this one didn't work, so what? Try it. Here's the next strategy that I can pick. Well, I know that, so write that down as my reason. And now suddenly I've discovered the technique I think that we need as teachers to. And if your first strategy doesn't succeed, importantly, I'm not going to spend 4, maybe 5 minutes total. So
we skip to good ideas.
Well, let's just quickly say one thing about part B. But again, when you have part B, show that KXMY is a parallelogram. First thing I would suggest is, well, actually draw in the lines that you need to make the parallelogram you're trying to work with. You know that you could work with diagonals, but that's probably going to be a little bit opposite sides equal, and those two opposite sides equal, or the opposite pairs of sides
efficient
parallel.
in the way you go.
The other side.
Yes.
If I look at 2 minutes gone. Okay, this is not working for me. I'm going to try another one.
Speaking of 2 minutes.
Teachers can do it on their own. I'm sure they can do it. Is a parallelogram. First thing I would suggest is you've only got 2 strategies. A little bit difficult, but it's down there as a strategy.
Yes, it is efficient
parallel
in the way you're going to solve a question. Yeah. Okay. Good gems in the past about group work. So expand on that for us.
Well, working in groups.
Potential if they're relying on other people to do work, or working with the help of others.
What it does require, though, is that you set in sort of large activities that will take sort of maybe an hour to do, maybe over several lessons to do, but you've got to have milestones.
Yes.
Found a barrier that they just simply as a group cannot get over.
It goes back to step 18.
Have the idea that unlocks it for the rest.
Yes.
And them having that idea, for lots of different reasons, I found it far better to have mixed groups, mixed ability groups, or the kids that I thought were better than some of the others. You find perhaps in geometry is quite reversed.
Yes.
So that's another thing to watch out for.
That Billy is no longer with them and pulls Billy in again.
Yeah.
Whereas if you're working individually,
is also really important in terms of how you're going to assess the output of the group. Sometimes you're going to assign formal marks to the output of the group.
Yes.
Sometimes you're just going to put them on the spot and have that group present its work or its together towards that common goal.
Yes.
Otherwise, the group is generally going to fall apart. So I would just have those two things always in.
And this just a little bit so we understand.
Well, this is this concept I advise that you don't leave it to this sort of 7 learners devise and develop their own geometry problems. It gives you a great source of geometry problems for the next year, but you'll be surprised at how difficult it is to set a really good geometry problem unless you understand all the points in the argument that you have to make for somebody to get the solution.
And obviously
done.
they'd have to provide you with
The written solution, yeah. And in that case, it's wonderful to give Group A Group B's rider, and have Group A discover something that was missing from Group B's.
Oh, fantastic.
Logic.
Saves on your marking.
Saves on your marking, but it also sets up some really healthy competition within the class. Can you construct a rider that Group A can't solve or has to take 2 weeks to solve?
Yes.
And as I say, in constructing riders that are that difficult, you really need to know your stuff.
Yes.
You really need to know all of your properties. You need to have a really good grasp of all of your tools, because unless you do, you're going to set a really simple rider.
And it comes back to backing up your arguments all the time.
Yeah.
If you can do that, then you can
If this, then that.
Yes.
If I can set a rider, I can solve a rider as another preposition you can put in there. Is my argument logical?
Yes.
Yeah.
Okay, Dylan, we have come to the end. Are there any parting remarks?
Have fun. This can be a really, really fun section. I think geometry, grade 10, grade 11, grade 12, can be an enormous blast in the class, because you can kind of get out of the strictures, the constraints of the rest of the curriculum, and just allow learners to have fun and explore and develop these kind of really, really essential skills.
Yes.
So have fun. I would say.
Have fun.
Have fun. Such fun.
Well, that's it. Remember that if you want to win a phone or a tablet, you should send through your teaching resource ideas. On teaching ideas, resources, anything you have, whether it's a video of you teaching or it's a worksheet or it's a website that you've used, send through instructions on how you've used it and how other people could use it, and you could win a Sony Xperia L or a Samsung Galaxy tablet. You've got to send it through to competitions@digitalclassroom.co.za, and we'll be watching out those submissions. Until next time, happy teaching. Goodbye.
Bye.
Created using Powtoon. Created